we thought we should now move to the second speaker of the afternoon, Robin Stinchcombe, who will also speak about symmetry breaking in statistical physics.
So I'd like to start by quoting Francois, quoting Harry Stern about escaping academic pedantry by having Robert Brout as supervisor. Well, I actually was one of those fortunate enough to see this element in the way that Brout could actually teach one in such a transparent and kind and generous way. When I arrived at Cornell in 1960 for a 2-year postdoc there. And I should say that the other teacher I had of enormous significance to me was Rudy Piles, who was referred to in the talk we've just heard. And so again, this was a tremendous thing for me to have met two such people. And in my case, the memories from the Cornell period, just like those from the previous 3 years of doctoral research, are still very, very vivid in my mind, even almost 60 years later. So I can't thank those two people enough for their influence on me. Now I'd like to go into this talk and say that there is a considerable overlap with the topics which were just in Edward Brezan's talk. And so he's dealt with some things much, much more comprehensively than I will have time to in mine, which is very, very nice. But I do want to try and give a simple theme which follows roughly a similar choice to those of Edouard Brezan. And so I'll just show you this line. On this outline. So you'll see here the very basic things which started Brezan's talk at the top here. And these were the things which were still being discussed when I first met Robert. And in that top section, then the next one were the models and the systems which were much to his interest and to others at that time. Then you'll notice that disorder comes into the next line when we're getting to more specific things, and criticality, and those were two of the things which Edward Brezan's talk gave examples of. So there will be an overlap, but my talk will be one which is trying to take a simple line where one sees some of the connections right back to the things which were being worked on when I first came to Cornell. The very last part here is just to give a slightly more modern thing to do with non-equilibrium systems. And I'll take, again, a very simple set of examples there. Now, these are the models again. And in the middle of this slide, you'll see, after models, it talks about constituents with pair interactions. So crucial thing is pair interactions in the next few minutes. And of course, the Ising model is the best known example of that. The liquid gas is very, very similar. There is a mapping, of course, because the variables, the spin variables, are analogous of being up or down to the two-state variables at a site in the lattice gas, which is the two states being occupation or vacancy there. However, Brezan's talk did warn us about trying to say they're entirely equivalent. There is an equivalence if you take a certain simple viewpoint. I won't dwell on that, but I will be trying to cut down some of the discussion by using equivalences as I go through things. And I'll come back to this aspect about large Z giving mean field theory in the next slide or so. Now in the bottom here, one has the Heisenberg model. Now that was covered beautifully, of course, this morning by Francois, and I was going to talk about the Goldstone mode and Francois' RPA, which he discussed in real detail. So I won't actually talk about those things, but I'm very pleased that they are discussed already today. Now here is something to get started, which was already happening in 1960 at Cornell. I think before Francois got there, but certainly in the first year or so, there were ideas to use graphical expansions. These are the many-body expansions in powers of the interactions. And so the graphs being used for the classical systems, like the Ising model and so on, were graphs in which the bonds represent interactions, so things called V down here, and the sites represent the sites of the spins interacting. So this, for example, here corresponds to a pair interaction between one site and another. Let's take it to be this one. And this is another pair interaction. This is a common site, so that's the I here. And this then could be a J and a K here. And we have this interaction here. Now, if you have pair interactions where the number of pairs interacting is Z, then this sum over J in here will be for a given I, it'll go over Z values. Likewise, the K is summed over Z values, and then I is summed over all the sites in the lattice there. So you see that this graph here picks up two factors of Z. On the other hand, this one here only picks up one factor of Z. And so the tree graphs, these ones here, are the ones which will have the largest factor of Z, and therefore they will dominate if the Z is large. So if the number of spins interacting with another spin is large, then you will get the tree graphs dominating, and they give mean field theory. Now this is a very simple point, of course, but it does give one then a way of treating systems in a systematic way, where you can start with mean field theory, which is simple of course always, and then use the next term, say the 1 over Z order term, to get the first fluctuation result and build it up in that way. And it was tremendously useful in the first days. Now, if you try and do the same with the Heisenberg model, which was in Robert Zann's talk, with a vector interaction, then the only difference, the same graphs appear, same geometry, but now you have operators which don't commute, so you need time ordering. So the job of we newcomers was to set the thing going for the quantum models, specifically the Heisenberg model, and all we had to do was put in the time ordering. But it did lead to useful understandings of, and again later, of more complicated quantum models, which are not as simple as the Ising one or the Heisenberg one. Now, I'm now moving on a bit more, but trying to keep some connection. Sorry, I'm going the wrong way. Yeah, with Robert Brout's work in the 1960s, we were hearing about the spin glass in the last talk, and Brout and his student Mike Klein actually gave what was the first mean field solution. Of course, the work of Sherrington and Kirkpatrick is far better known. That was 12 years later than this work here, and again it was a mean field picture. So the real advance was later on with the Parisi work, 20 years after the after this here, on the spin glass, where the replica symmetry breaking we were just hearing about was given in Parisi's work there. Now, I just want to move on a bit more. By these sorts of times, into the later 60s, one was seeing lots of equivalences between models arising. There was a class of models called the Potts models, which could have any number of states, and the two-state Potts model, S equals 2, it's in this graph, is the Ising model. It was Castellane and Fortune in these papers proved lots of equivalences between thermal models like the Ising models and cluster models. And so, for example, one of the cluster models is a geometric model which relates to connectivity, and that's the so-called percolation model. And it is related to an S-state Potts model with S going to 1, actually. So one's now being able to build connections between various sorts of models. Another connection, which came just a little later through work of Suzuki and others, involved relationships between classical models like the Ising model and quantum ones. Now, in Edward Brezan's talk, he spoke about equivalences in disordered systems. The random field model was the one he was taking, and there was an equivalence, or was a proposed one, between the random field models and the Ising model itself, with dimensions different by 2. Now, in this relationship I'm referring to here, this is a relationship between Ising model and a quantum model, actually in one lower dimension, it turns out. And it just comes from some mathematics involving a so-called Trotter formula, which is a way of expanding a function of a discrete variable, an exponential form actually, and seeing the connection with the lattice-based variables. And the point is that this is a quantum model, and it can have even a transition at 0 temperature. And then you find that the relationship between the models, as I say, differs by 1 dimension. So the phase transition in the ordinary two-dimensional Ising model becomes a phase transition in one dimension in the quantum system. And this is a phase transition not in as you vary T, the temperature, but as you vary a parameter in the quantum model, which is actually a transverse field. So the relationship is between an Ising model, an ordinary one, and an Ising model in a magnetic field transverse to the usual ordering direction. So now, these systems are very, very nice to work with, and so they're among the quantum systems that we could use the Heisenberg-like expansion, many-body expansion I was referring to earlier. So, so these are connections I'm trying to establish and were used. Now, I want to talk a bit more about percolation. Let's go back to this slide. If you take a lattice of bonds and dilute the lattice by taking out bonds at random, if you take just a few bonds out, sorry about this, just a few bonds out, then you get things, forms like this. This still is a case where there is a connectivity from one side to the other, because there's a path going all the way across that way, and also this way here. So, whereas if you look at a more diluted case here, then what you're seeing is a lot of finite clusters, none of them spanning the lattice. So if you take a magnet and dilute the bonds, or the spins even, then you could move from here to here, and as you go from one type to the other, the magnetization has to vanish, because one needs a very large system to get spontaneous magnetization, as we've been, again, hearing in the previous talk. So this is a case which is another transition, and the vanishing of the magnetization happens not by changing the temperature, but by changing the concentration of bonds through some critical concentration, where you go from here to here. Now, I would like to now change gears slightly, but I'll come back to this model to use it in a certain context here. The next thing I wanted to say relates to the fact that this 1 over Z expansion, which works so beautifully if you're just moving from mean field to fluctuations or more fluctuations, when you get in a certain situation, it breaks down and it's not very useful. That situation is the case where you're close to the critical point where the correlation length diverges. You see, when Brout set up the 1 over Z expansion, what he was doing was comparing two lengths, really. One was the lattice spacing, the basic length in the system, and the other one was the range of the interaction. Now, if you then find there's a third length in the system, you have to allow for its effects. And it's known, and that was referred to, of course, in Rezan's talk, but when you get close to the critical temperature, when you have a continuous transition, the correlation length becomes very, very long, and at the critical temperature itself, or in the case of a case where the criticality is at some critical concentration, at that concentration, you'll find this length has diverged. correlation length diverges in these continuous transitions at the critical point. So there is a third length in the system, the correlation length, which can become very large or infinite, which is the scale invariant case. Now, that is the reason why the 1 over z expansion breaks down. It's because of the existence of this third length and its divergence. And so, as was said in the last talk also, this needs other procedures than these sorts of simple many-body expansions. And of course, the way it's dealt with is to use the scaling and renormalization group procedures. So what I'm going to do is demonstrate in a very, very simple such procedure by using the percolation transition as the case in point. So let's just look at what happens exactly at the critical point in percolation. Here is the situation at the critical point itself, this critical concentration. And if you ignore the smallest scales, there's a definite smallest scale, and look at everything else, you can perhaps see that there's a sort of scale invariance. It looks the same on all scales, except when you get to this very small scale thing. So that's an example of a diverging length and self-similarity. If you look at this and pick out different parts of it and expand it, it looks the same as the main picture. You know, the same in the sense of looking at a similar sort of pattern. So we do have here the diverging length, and to treat this problem, one has to get a handle on it. And as was mentioned in the last talk, that handle is provided by the scaling procedures, which Wilson found a very, very nice way of exploiting, which is called the renormalization group of transformations, and which already Leo Kadanoff had seen one had to exploit somehow. And so his ideas were we need scaling so that we can make our comparison of lengths, correlation length compared to the lattice spacing, get to a simpler value than the very large or infinite value at the critical point itself. So the idea was to rescale the lattice and to see how the parameters, like temperature or concentration in the case of percolation, how those parameters scale. And then that gives rise to a set of transformations, which are the renormalization group transformations. And that those transformations depend on the actual value of the critical, of the concentration or temperature. And then there will be a fixed point where the system, where the parameters don't have to scale, and that's the case where you already do have self-similarity because you're at the transition. So, so again, as was explained in the last talk, the way one understands the properties that are seen, namely universality, where things don't depend on lots of the parameters at all, that can be seen through these sets of scaling relations. So here's an example here. Here, which imagine you have a setup where there are two parameters in the system. Then if it's an Ising system, they could be the nearest neighbor exchange or and the next nearest neighbor exchange, for example. And then under scaling, you typically find an unstable fixed point, which is where, from the point of view of this parameter, things are scaling into the point. And from the point of view of this parameter, so that's a k, there is a instability here. And then the lack of dependence on parameters is this business of universality. So what I'm going to do now is just demonstrate for the case of percolation a very, very simple way in which one can see some aspects, qualitative ones only in this case, of scaling by looking at the percolation transition. So now there's a procedure for percolation which Kadanoff and Tony Houghton and we used, and also Migdal in Russia independently had found this sort of method. It's called decimation, and all it does is to transform the lattice to one which, with a larger scale, by simply removing sites. So if you, for example, remove all the sites without a cross, this one, this one, this one, and this one, then these sites all remain, and the bonds which connect them would be ones there, 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 and there, obtained from connectivity through a path like that, or a path like that, through the sites which have been decimated. So this is the way one does very, very simple scaling. So we'll then be finding that the concentration P, which determines the connectivity, so for example in this here, you will have a connectivity from here to here via that path, and also you could have both paths. Now to avoid over-counting, we could just add up the probabilities of going from here to here on that path and not going that way, which is a p squared, probably this bond and this bond are both there. Whoops. And not this path means 1 minus p squared, and you get two things like that. And then having both paths gives you a p to the fourth. You add those up, they're independent events, then you get this result for the transformation. And this has a fixed point, as we were talking about, namely a value of p which transforms into itself, which is somewhere between around 0.5 or something. And that gives you the estimate in this simple approximate scheme of the critical concentration. And if you then look at the scaling of the parameter p close to the fixed point, you can get the critical exponents and so on. Now, all these things are very, very well known, so I apologize to a lot of you who know everything I've said and much more, but I hope that for some these sorts of things can be of interest. So now, I just want to and make one further point. This is very, very approximate because, of course, when you do this decimation by taking out these sites here, you get not just the connection between this site and this one, but straight away one from there to there, because there's a path there. And so what's happening is the parameter space is enlarging, therefore, to actually treat this problem properly, you have to allow for the fact that your scaling procedure is building up more and more connections, and you have to then allow for their scaling. The whole group of parameters have to be scaled. If I go back to this slide here, then if you think of the case where this is a parameter related to the nearest neighbor bond being present, and this one to the next nearest neighbor bond being present, then you can see that this is a way of seeing how you deal with the enlarged parameter space and treat the problem more properly than the limited procedure I was giving allows you to do. Now, what I'm going to next do is to move on a bit to something much more recent, and one of the examples that I've been working on more recently, which is non-equilibrium systems. In Brezan's talk, he started with saying how one treats systems in equilibrium, and those were static or non-evolving systems. Now, if you then try and look at non-equilibrium systems, if they're stochastic, like the equilibrium systems that Brezan was talking about, then you have probabilistic things to look at, and the way of looking at stochastic dynamics is using a master equation, where you start with if it's a classical system, in some configuration, then what you set up, the ways of moving in and out of that configuration, and putting the rates into a linear equation, which is called the master equation. Now, you can generalize this very easily to quantum systems, and you could equivalently take classical systems and write down a quantum equation, the one which looks like ordinary quantum dynamics, with a Hamiltonian there. So you can transfer the classical systems to linear equations which look as though they're coming from the effects of a Hamiltonian on the quantum system, changing the states, which is what the configurations have been turned into. Now, because these systems are normally relaxing to an equilibrium, the Hamiltonian is normally, it doesn't have to be, it's normally non-Hermitian. There are cases where it's not. So if we look, for example, at the lattice gas, it came up in Brezan's talk and was on one of those slides earlier here. One here could have particles or vacancies at the sites of a lattice with specified rules for a given model of how the particles move from one site to another. And so if you take a linear chain as the very simplest example, you could have a chain of sites on which there's either particles or vacancies, never more than one particle on the site, and have a hopping, say, just to the right on that lattice, as long as you exclude double occupancy. So you can only hop from one site to the site on the right of it if the first site is occupied and the second site is empty. So that is a certain very, very simple model, which is called the TASEP, totally asymmetric exclusion process. And the exclusion is excluding more than one particle from a site there. And that's the very easiest system of all to write down, but it's not trivial to deal with. And what I'll show you in a moment is how one can deal with it in a mean field-like way. And it'll turn out that the mean field theory, even in this case, can give exact results, which can be of some interest, actually. And I'll show you an example of its use on that TARCEP system as a traffic model, and then we can talk, if there's time, a bit more beyond that. So now, here we go to the TARCEP process. The upper diagram here, this one here, is just illustrating that rule I talked about. So if this is if black means occupied site, open circle, unoccupied one, then according to the rule, which was hopping from a vacant site into one which has not already got something there, this is a step, an update which is allowed. That is the update which is allowed. This one is not allowed. That's what the X means, not, because this would hop onto one already occupied, and that would violate the exclusion rule there. So this is the internal process for the one-dimensional TARCEP. Now I'll come to the fact that there can be open boundary conditions, which their effects are very interesting. I'll come to that in a moment. But if we just have this on an infinite chain, then you can see that it's a very, very simple process. And you can write down a quantum form for this and try and solve it. And it's really rather hard. But there is a way of solving this problem here using a beta ansatz. So it's not trivial even just having the nothing about boundary conditions coming in. I'm going to not do that. I'm going to just go for a very simple mean field solution. And I'm going to just look at the steady state. And the steady state is where the system's got into some state, and it is the state which it sticks at. Even though there's motion going on, it's the same configuration from one time to the next. That means that that the occupation, which I'll call rho, at site L, I'll call this site L, say, L+1, that occupation is not changing in time, which means that there can be no net particle current into the site. In other words, if you're in the steady state with the occupation fixed, then this current of particles has to be equal to this one. So now that then allows one to get further on with seeing what the steady state is. And if you make an approximation which is to ignore the correlations between the occupancy of a given site L with L+1, then that's you're factorizing a correlation function actually. Then it would be just that this rule for hopping here involves on this bond here a current which has to have particle here and no particle there, which is this has those things individually. Particle here has this probability, occupation probability, and this is 1 minus an occupation probability. That would be the probability of the next site being empty. So 5 minutes, yeah, okay. So in that way you get here a statement in mean field about the relationship between the rho L's, and you can use that to find out rho L in terms of rho L itself, and that's gives one rise to a profile map. And if you then run this relationship, then you find that the profile is increasing in this way, and we'll go into this point here. For this case, I'm showing in the map the actual form of the profile map one has for J current less than a quarter, equal to a quarter, or greater than a quarter. So you see profiles which look like this, density profiles that are going down the system, or like these, depending on the value of J. Now, those things I was showing here about the boundary conditions, they are the ones which actually determine then what currents can be, and then tell you whether you're into this situation at the top or these here. These are Tanch functions, by the way. Now, if you've ever been on a motorway or autoroute, and you found the traffic you've suddenly moved into a situation where it seems to be slowing down enormously, your speed has gone down because the density is high and so on. That's typically because you've moved from being in an area like this to one like this of higher density. And you may think there's a collision ahead, but it need not be, so it's just this sort of change which is maybe going on. And the way, of course, the traffic controllers deal with things is to try and keep, by traffic lights and so on, the speed of cars down so that you're into this situation here, the low current, sorry, not into this situation here, because then if the car speed has gone down and you have a current close to the maximal one you can have, which is actually this J quarter, then that is the best from the point of view of the driver. So I'm going to have to finish quickly now. I should say that so this is the actual phase diagram showing you what currents you can have as a function of alpha and beta. So the thing you really want to be in is this bottom left situation. There are beautiful ways of dealing with this problem given by Derrida and Company, which preceded the beta ansatz solution I talked about. And there are very nice symmetry breaking models, e.g. for traffic coming on a two-lane highway with cars moving in opposite directions and meeting bridges and so on. There's some lovely ones like that. If anyone wants more on this, there's a review at the bottom here. But I don't have time for more, so I'll finish here. But I do want to end by saying that it may not have been obvious from the way I gave the talk, but there has been a very, very large influence in the way that I see myself looking at things, and plenty of others as well, which is the sort of thing which I learnt really from, especially Bob Brout, but of course Francois as well was hugely helpful in guidance in those early days. So I'd just like to finish by giving a thanks from myself to those pleasant days in Cornell in the early 60s. So thanks very much. I'll finish there.
Thank you very much. Questions? Yes?
To the microphone.
Has anybody looked at two-dimensional model
Yes.
for this?
Oh yes, indeed, yes. There are. Yes, that's a very good question.
But it would not be solved by Betty answer.
So what?
It wouldn't be able to be solved with
No, that's
Betty
right. The
answer.
big ansatz is really one-dimensional. And indeed also this matrix ansatz. With ordinary matrices, the matrix ansatz is set up for one-dimensional cases. And the mixed ansatz involves using two matrices in this case. One is for vacant site, and the other is, they call them the C and D, D and D, one for vacant site and one for occupied site. and then you write down a string of operators and in between wave functions, and that string represents the configuration. So DEE would be particle vacancy, 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 and then you can have an algebra which gives you the right solution. Now, if you try and take that to dimension, it becomes harder, but it is possible to write down matrix ansatz in the generalized form. Thanks.
Well, if there is no other question, let's thank our speaker again.